Welcome to Getting Started with Mapping in Tableau. This video covers the various options for mapping and using background images in Tableau Desktop. At its core, geographical analysis comes down to plotting points. The map image provides the background, and coordinates are plotted on it. Latitude indicates how far up or down from the equator. Longitude indicates how far east or west from the prime meridian. Any point on a map can be represented with latitude and longitude coordinates. In Tableau, coordinates need to be in decimal format. Positive latitudes indicate the northern hemisphere. Positive longitudes indicate eastward from the prime meridian. In this way, every point on the globe has unique latitude and longitude coordinates. Incidentally, Tableau uses the same projection as Google Maps, which is Web Mercator. If your dataset has latitude and longitude fields, Tableau can automatically plot them on a map. On the other hand, if your data doesn't have latitude and longitude, but you have geographic place names, such as city, country, or province, Tableau will determine their coordinates and provide the fields latitude generated and longitude generated. If your data contains locations without latitude and longitude coordinates that Tableau cannot recognize, you can add to the database and enter your own custom geocoding, or simply blend in the geographic data. The videos, expanding Tableau's mapping capabilities, and custom geocoding go into more depth. Locations can be plotted on a map in two ways: as a point or mark to represent the entire area, or a polygon covering the area. Tableau has polygon data, or filled maps, for many geographic locations built in. It's also possible to provide your own polygon data to create custom polygon maps, such as this map of national parks in the UK. Check out the Polygon Maps video for more information, including creating custom territories on maps. If the default map tiles aren't what you need, maybe your analysis is of ocean currents, Tableau offers the option for connecting to Mapbox or a web map service. There's a video on each of these options. If you need to do something like plot the location of cavities on a dental chart, you can upload an image directly and assign it coordinates, as shown in the background images video. The options for geographic analysis in Tableau are extensive and powerful. There are many options for customization to make sure your analysis needs are met. Often analysis involves geographic data, whether it's what countries a student body represents or flight delays in different cities. Tableau has a robust internal database that can recognize common geographic field names, such as country, state, and city. And the data pane will automatically label these fields as geographic roles with a globe icon, like here. If Tableau doesn't automatically recognize a field as containing geographic data, it's very easy to set that. Simply click on the icon, select Geographic Role, and select the correct type of geographic information contained in the field. Once the field has that globe icon, Tableau will generate latitude and longitude coordinates for the geographic data. By default, when we double-click on a geographic field, Tableau will plot it on a map, automatically putting the generated longitude and latitude fields on columns and rows respectively. Adding state is as easy as dragging it out and dropping it on the map. Both of the fields we've mapped so far have defaulted to symbol maps. Symbol maps are where a mark, in this case a circle, is used to indicate the location. These marks can be modified. Here we can change the mark type to shape, click on the Shape shelf, and choose our desired shape. We can adjust the size and bring something like Market to color. These marks are just like the marks on, say, a scatter plot. They just happen to be plotted on a map. Some geographic types, such as city, can only be represented as symbols. However, geographic types like state or postal codes can be represented as field maps in addition to symbol maps. we'll switch the mark type to Filled Map, and it's as easy as that. Filled maps can be created by changing the mark type, like we just did, but let's undo that, or by bringing a measure, such as profit, to color. The mark type has to be automatic for Tableau to switch to the filled map automatically when using a measure on color. Filled maps cannot encode anything by size, as the sizes of the areas are established by the geographic data. Tableau's default maps are grayscale. However, we can customize maps. Go to the Map menu and click Map Layers. The Map pane comes up covering the data pane. We can control the background. The style, here, can be normal, which is a blue water style, light, like we see here, or dark. We can control the washout, as well as add map layers. Let's turn on coastline. Though several options, such as streets and highways, are currently grayed out. This is because we're zoomed out too far. We can search in the map, say for Dunedin, New Zealand, and we could zoom in using the Zoom tool. Now Streets and Highways is available, and we can turn it on. The View toolbar has zoom controls, the ability to pin or unpin the map, and controls for zoom selection, the pan feature, and various ways to select marks. However, we may not always want these options to be available. To customize map options, click on the Map menu, Map Options. Here we can turn on or off pan and zoom, the search option, and the View toolbar. If we don't show the toolbar, the mouse behavior is whatever we last selected, here the radial select. Make sure you set what the mouse should do before you hide the toolbar. Note that hiding the toolbar doesn't turn off the pan and zoom via keyboard controls, such as shift dragging to pan. If you want to fully disable those features, make sure you specifically turn them off in the map options. Map options allow you to fully control how users can interact with your map. By default, when we double-click on a geographic field, Tableau will plot it on a map. In this dataset, however, double-clicking city ends up with a lot of unknowns. That's because there are many cities which could be in one or more countries. For example, there's an Aberdeen in Scotland, Sierra Leone, South Africa, and that's just S countries. To resolve this, we simply need to add state and country to the view. It's as easy as bringing these fields to the level of detail shelf. If there is a hierarchy in the data pane, Tableau will automatically use the appropriate levels of the hierarchy to solve ambiguities. Note, we only brought in state, but it automatically brought in country as well. Now the map has access to the additional information of state and country, as well as the city's name, and it can correctly map the cities in their appropriate locations. As a takeaway, if there are ambiguous values, such as multiple cities with the same name, try adding the next higher level of the geographic hierarchy to the map. Sometimes, however, these unknown locations can be prompted because there's a misspelling or some other issue. Here we have 8 unknowns. We could right-click and hide the indicator, or, when we click on the indicator, we're presented with several options. Edit the locations, filter the data, or show the data at a default position. We don't want to ignore any cities where we have data, so let's edit the locations. This dialog box is really powerful. Let's work our way through it. The first option is country. This can default to whatever the physical computer's country is, like mine did at first, assuming all the cities were in the US. If we don't want to bring our country field to the level of detail shelf and we haven't built a hierarchy, an alternative is to come here and tell Tableau to take the country for each city from a specific field. And we could do the same for state. However, we still have some issues. If we're on the State tab, we see an unrecognized value. Due to the 2014-2015 territorial reforms in France, Auvergne is no longer recognized. We can click in the box and start typing the correct place name. and we'll select the correct option. Fixing this state issue corrected most of our cities, but we still have two issues. For one, there's a spelling mistake. Fortunately, I know that Philadelphia has only one L at the beginning. We'll do the same thing. Let's click and start typing the correct spelling. There it is, Philadelphia. For our final error, we have Tangering listed as unrecognized. If our dataset has a location that isn't in Tableau's database, such as this city, but it's not worth doing full custom geocoding, we could simply come here and enter the latitude and longitude for that city. Now all the locations have been appropriately edited to reflect the underlying data. It's possible to get to that dialog box by going to the Map menu and choosing Edit Locations. Spatial files contain geographic information that can be very useful for visual analysis. Tableau supports point geometries, linear geometries, or polygons. It does not support mixed geometries. To begin, we'll connect to data. In the Connect pane, click Spatial File, then navigate to the file itself. Tableau can connect to a variety of file types, including Esri shapefiles, KML, and GeoJSON. Once we've connected, we can see the data in the preview grid. Tableau interprets the spatial information as a new field, geometry. When we click to a new sheet, we see that geometry field has a globe icon, indicating it can be mapped. If we double-click, we get a map. That's how easy it is. By default, when we first map the spatial file, it comes out as a single mark, as we can see in the bottom left corner, or by hovering over the map. We can begin disaggregating the data by adding another dimension to the view. Let's bring road class to color. Now we have a sense of the types of roads. We can see the freeways clearly, and that most of the roads are local access municipal. When we hover in the view, we see all roads of that type. Alternatively, we can disaggregate the view entirely by going to the Analysis menu and unchecking Aggregate Measures. This breaks the data down into its basic units, here road segments, with each getting its own mark. But I want to see each road as a mark, even if it's made up of multiple segments. So I'll undo that and bring road name to detail. I'm curious about road types, so I'll switch that for color. And I'll sort by the number of road names. I'll assign the summer color palette, but make the long tail gray. It looks like Court is most common by number of roads, but they're all pretty short neighborhood roads. Whereas streets look like they cover more ground. And roads tend to be pretty long. Interesting. We can size by something like speed limit. Let's make it a number and convert it to a measure. And then bring it to size. Uh-oh, it turned our lines to points. If we change the mark type back from automatic to map, we get our lines back. But that's not as interesting, so I'll drag it off. I have another data set I want to bring in here about trees in this city of Brimbank. The trees data gives the site name for the tree as the name of the road, so we can use that to join these data sets. We'll make a left join on road name TY and site name. Spatial files can be joined just like any other data. A common need when working with location data is to work with data that falls inside a given boundary. For example, looking at oil well production within a certain drilling zone, or contaminated products in a distribution area during a recall. However, this data is often captured and stored differently. Point data, identifying the specific well production or contaminated product, and polygon data, identifying the drilling zone or distribution area. In order to perform analysis of this sort of spatial aggregation, the spatial files must be joined. Here we have two datasets. The first is watershed basins in Japan. This is our polygon data. Second, we have sightings of waterfowl as point data. There's no shared field between these datasets. The watershed basin is not recorded in the waterfowl sightings. However, they're both spatial files, so we know the geographic outline of the basins and the geographic information for each bird sighting. We want to be able to analyze the number of birds seen in each watershed. To do this, we'll join the data. First, we'll connect to the watershed data. Here, we're adding a net new data source by going to the Data tab and selecting New Data Source. We'll choose Spatial File and connect to the basins data. Because they're in the same folder, the waterfowl sites is also available under the Files area in the Connections pane. We'll drag this to the canvas, and now we're able to set up our cross-database join. In the Join area, we see that Tableau has identified the two geometry fields, the only information that is shared between these data sets. To establish the spatial join, we need to verify that the join condition is intersects. An intersect join clause matches when a point is inside the polygon. Note that only point-polygon spatial joins are supported in Tableau at this time. Finally, so as to keep all the watershed basin polygons regardless of bird sightings, we'll change this to a left join. We've just recreated the dataset that's used in this joined data dashboard. And we can proceed with our analysis as with any data. It's easy to work at either level of geometry, polygon or point, and see how they're related.
Heat maps are a fast and easy way to visualize patterns in dense data. Heat maps use the density mark type, which can be used on both maps and non-maps. Let's see how this works in Tableau. Here, we're looking at data on over 300,000 taxi pickups for the month of October in Manhattan. This map shows every single taxi pickup instance represented by each mark. Notice that the default mark type being used here is the automatic mark type. We can see that the majority of the marks seem to be clustered here in mid to lower Manhattan, with fewer rides up north. But it's difficult to understand which specific locations have greater or fewer numbers of data points, since there are so many overlapping marks. Heat maps make it easy to see these concentrations in your data. All we need to do is change the mark type from automatic to density. And just like that, we have a heat map. Tableau does this by grouping overlaying marks and color-coding them based on the number of marks in a group. Now we can instantly see concentration areas where more taxi pickups occurred. I can choose a color palette that is designed specifically for displaying density, or I can choose one of the existing color palettes. The more overlapping data points, the more intense the color is. Note that I do not have the normal option to edit the individual colors in the palette. Custom color palettes, however, can still be used. I also have the ability to adjust the opacity and intensity of the marks, with intensity allowing me to show more or fewer hotspots in the data. And I have the ability to adjust the size of the density marks as well. Notice that there is no color legend for heat maps. The palettes are designed intuitively to show relative densities, with more concentrated areas appearing brighter and more intense, and relatively less concentrated areas being less intense. Density is also dynamically displayed, so when I zoom in, Tableau will recompute to show the relative density for the new view. Finally, I have the option to add weight to the density, meaning that I can define how the density is being computed. For example, right now the hotspots in our heat map are showing high concentrations of the count of taxi rides. Let's see what happens when we weigh the density by toll amount. The hotspots now show where trips with higher tolls originated. Note that only measures can affect the weighting of density. This mark type isn't just limited to maps. As we've seen, density can be applied to any chart type with a large number of overlapping marks, such as dot plots or paths between origin and destination. A common use case, however, is on a scatter plot. This scatter plot shows a common sales versus profit scenario, and it is dense data with many overlapping marks. In the same way as before, we can change this to a heat map by simply changing the mark type to density. Notice that when I hover, I can still interact with the underlying marks to view the tooltip detail, and I can select those marks and interact with them as I normally would. One powerful application is combining density with the date filter to see changes in density over time. Going back to our taxi data, I'll bring pickup date to the pages shelf. And now, as we step through the pages, we can visualize and compare patterns in taxi pickups by hour.
It's possible to expand the mapping capabilities of Tableau and map data that goes beyond what is automatically available. For example, if we wanted to look at global branches for Bank of China, these can be mapped using coordinate data. If our data has latitude and longitude coordinate information, that's all we need. Here, for example, we have branch information for Bank of China branches outside of China itself. I pulled the addresses from boc.cn, then ran them through a batch geocoder using the link available under the video. Now the data has geocoded information for each branch. We have these fields, latitude and longitude, from the dataset directly. We'll plot these by double-clicking. Let's bring branch to label. And now each record from the dataset is plotted, and we see a dot for every branch. If we had banking data for these locations, we could blend or join in that data as long as there's a shared field with our geocoding dataset, such as branch name or address. One of the big distinctions between using geocoded data directly and importing custom geocoding is the ability to use polygons, or filled shapes. If we connect to a data source with polygon information, it's easy to map custom polygons. I'll run through a quick example here, but for more information on the necessary data formatting and detailed steps, please refer to the video on Polygon Maps. We'll change the mark type to polygon, bring park name to detail, point ID to the new path shelf, polygon and subpolygon ID to detail, and for the big reveal, plot latitude and longitude. That's been two examples of using data that contains latitude and longitude within the dataset, both for points and polygons. If we don't want to deal with latitude and longitude in the data every time, we can import custom geocoding into Tableau. The basics are fairly simple. First, we need to create a custom import CSV file or files containing the geocoding information. These files need to be set up very carefully. Please see the video Custom Geocoding or the online help for more information. Next, we import the folder containing the CSV files into Tableau. And last, we assign the geographic role to the field within Tableau. Importing the file is easy. Go to Map, Geocoding, Import Custom Geocoding. The zipped folder is available for download under the video. Browse to the folder and select Import. Note that Tableau will import all CSV files in that folder. Now our geocoding has been imported, and every time we create a workbook on this machine with a dataset that includes branch, all we need to do is set the geographic role, and we can map it. Here we're connected to some simple dummy data that contains the bank branch name and some made-up information about employee counts and manager. There's no latitude and longitude directly in this dataset. Tableau has not automatically recognized this field as a geographic role, but we can assign it. Click on the ABC in front of branch and change the geographic role to the new one, branch. Now this field has a globe icon in front of it with a symbol indicating that this is a custom role. We'll plot country and then branch. And here's our map, done without latitude and longitude in the dataset itself. Maybe we'll color by number of employees and add manager to label. There are three main types of custom geocoding: extending an existing role, adding new roles to an existing hierarchy, or adding new hierarchies. Regardless of the type of custom geocoding, the CSV import file must be created very carefully. It must have consistent spelling, capitalization, and column names. For example, latitude and longitude must be spelled out fully and be capitalized. Extending an existing role would be the option for adding towns that Tableau doesn't automatically recognize. Here's a CSV file which adds in some small towns from my home state of Florida. I have to indicate every level of the hierarchy above the cities, so state and country, then provide the latitude and longitude for these new cities. Because all three levels of the hierarchy are existing roles already in Tableau, I have to name my columns exactly as Tableau knows these roles. The online help has a table with the column names to include. Adding new roles creates new levels within an existing hierarchy, such as adding Bank of China branch locations under the level of country. If we also had both city and state information, we could nest branch under the city level. However, if, for example, we don't have state information, we can't simply go country, city, because that's not an existing hierarchy. To add a new role to the existing hierarchy, I have country, then branch, then the latitude and longitude. Once this is brought into Tableau, branch will show up as an entirely new geographic role. Adding new hierarchies would be useful for situations such as mapping custom sales regions, covering theater and region. These are not existing roles, so it's a brand new hierarchy. To create this, we need to make a CSV file for each level of the hierarchy. Because we could individually map at any level, we need latitude and longitude coordinates for each level. If we look down at region at the bottom, we see that it contains all the levels above it, so Tableau knows precisely where each piece goes. Make sure to save all the CSV files for the various levels of the hierarchy in a single folder. To bring in multiple custom geocoding files simultaneously, it's necessary to save all custom geocoding CSVs in the same folder. Let's import those two CSVs we were just looking at. Go to the Map menu, Geocoding, Import Custom Geocoding. The folder can contain as many CSV files as necessary, but the entire folder will always be imported as a single entity, and if a workbook is packaged, all custom geocoding data will be bundled with the packaged file. Packaged workbooks that contain custom geocoding can have their custom geocoding imported into the local repository, but that will replace any existing custom geocoding on that system. To import the custom geocoding from a packaged workbook, we'd select Import from the current workbook. But we'll just import from the folder. This may take some time, so I'm going to pause the video. To use custom geocoding, the dataset simply has to have the same field that's been added to the custom geocoding. Here we have Florida small towns. and the end user interacts with these fields as if they were any other automatically recognized geographic role. We'll double-click City and add description to Label. These towns are too small for Tableau to have recognized without that custom geocoding information. Tableau's Filled Map feature creates Polygon maps quickly and easily. We simply double-click on the geographic field of interest. Here we'll use Country. This defaults to a symbol map. If we add a measure, like profit, to color, Tableau automatically makes it a filled map. However, if we switch and put a dimension, say market, onto color, we have a symbol map again. We can force this to be a filled map by changing the mark type. Sometimes our maps need custom territories. For example, perhaps we want to do analysis in Africa based on time zone. Each country, except the Democratic Republic of the Congo, falls into just one time zone. So here we have a map at the level of country. To create our custom time zone-based territories, simply select the countries that make up a territory and group them. Repeat to identify each territory. Please forgive any inaccuracies here as I select, and I'm putting all of the DRC into Central. I'm also speeding this up. Notice that the grouped field shows in the data pane. This field functions just like any other group. See the video on grouping for more information. Now, because we want to use just the time zones, regardless of specific country, we can remove country from the view and just use those custom territories. Multiple custom territory groups can be created and even nested. To learn more, refer to the online help. What if the analysis we want to do requires non-standard geographic areas and custom territories won't work? To map those areas, we need coordinate data and information on how to connect the coordinates. Certain fields are required to create a polygon map. I like to think of it as a series of connect-the-dot drawings where each polygon is a separate drawing. The dataset has to contain specific information for Tableau to know what lines to draw and where. Latitude and longitude are the coordinates of each point in the polygon, or each dot in the connect-the-dot. The point order field tells Tableau which dots to connect and in what order, like the numbers on a connect-the-dot. The Polygon ID field will identify individual enclosed areas, letting Tableau know which points make up each drawing, essentially when to lift the pencil. This can be as simple as the name of each area. The key point is that each polygon needs a unique identifier. Depending on the complexity of the polygons, it might be helpful to have sub-polygon IDs as well. Multiple enclosed areas can roll up to a larger area. For example, Greece has many islands, each of which would be their own polygon, but on a world map, we'd want to know that all those islands roll up together with the mainland into a single country. TableauMapping.bi is a great resource for polygon data, and the dataset we're about to use is from their UK repository. Now that we know what the data needs to look like, we can start building that polygon map. Here we're connected to polygon data for the national parks of the UK. If the ID fields are showing up as measures, simply drag them into the dimensions area of the data pane. This is a key point. This forces Tableau to treat these measures as discrete instead of values to be aggregated, as measures would be. Next, change the mark type to polygon. Bring point ID to the path shelf. This connects the dots in the dot-to-dot we're drawing. Place the Polygon ID field on the detail shelf. This breaks up each set of points into individual polygons. If present, we'll do the same thing with sub-polygon ID. Next, we'll plot the latitude and longitude coordinates by double-clicking. Finally, drag the unique identifier for each polygon onto the color field. In this case, that's park name. And here we see the UK national parks. Maps are beneficial to many analyses. and Mapbox lets you customize maps beyond what Tableau's built-in capabilities allow. Let's get started. First, we'll double-click on Country. This maps onto the default Tableau map. To change it to a Mapbox map, click the Map menu, Background Maps, Map Services, and we need to add a Mapbox map. Let's start with Mapbox GL. Name the style. I like saying M, then the style name, so I know it's from Mapbox. We'll call this M Blue Green. Then enter the URL. When I hit Tab, it will automatically populate the other fields. We could also use a token and fill the fields out manually. There it is. For Mapbox Classic, it's very similar. We go to the Map menu, Background Maps, Map Services, and add a Mapbox map. This time we'll click to Classic. Again, we need to name the style. We'll call it M Pencil. And next we need an API access token. Finally, choose a preset style from the drop-down. Ta-da! The underlying map has updated to the pencil style. But what if we wanted to go back to M Blue Green? Using the Map menu, click Background Maps, and we can see the default Tableau maps as well as the Mapbox ones, and it's easy to change between them. A web mapping service is a way to share map images over the internet. A WMS server provides the tiles that make up maps in Tableau. Connecting to a WMS server may be useful if you're looking for an alternative to the default maps that Tableau provides. To connect to a WMS server, go to the Map menu, Background Maps, and choose Map Services. Click Add and choose WMS Server, then enter the URL. There are many publicly available WMS servers, or some companies have their own infrastructure. Note that the speed at which these maps render depends on the server that you're connecting to, as well as your network connection. Next, plot the data just like normal. Here we'll double-click on Country. If the map ever doesn't look how you expect, check two places. First, go to the Map menu and Background Maps and verify which map you're connected to. Second, check out Map Layers. Some WMSs have a lot of layers, so this is a good place to look and explore options, including deselecting any layers that may not be working properly. As a note, it's possible to connect to many WMS servers in the same workbook. You can use as many as you need. If we want to save a WMS connection for use with other workbooks, we can create a Tableau map source file. Go to Map, Background Maps, Map Services, and select the map we're interested in, then click Export. The file type is saved as a .tms file. Instead of Export, I'll click Import. I'll open my Tableau map source file, and it's automatically applied to this view. Let's add some layers. We'll add countries, maybe water bodies, rivers, and streams. Tableau can bring in background images and plot data over those images like a map. The basic steps involve importing the image and specifying a coordinate system by mapping both the X and Y axes to measures in the dataset. Adding an image must be done in regards to a specific dataset. For this video, we'll work with the Hong Kong MTR system. Here we have a partially completed Excel file with the line and station data, as well as placeholder columns for X and Y. As a note, Tableau needs things formatted in certain ways to bring in background images successfully. the X and Y fields need to be measures, and there needs to be a scale assigned to each axis of the image. The specific steps we'll follow in this video are not necessarily requirements, but they make the process work smoothly. Before we do anything else, we'll record the dimensions of our image in the X and Y columns for our spreadsheet. Our image is 840 by 623, so we'll enter that and save the spreadsheet. Now in Tableau, we'll connect to that dataset and click on the sheet. Next, go to Map menu, Background Images, and click on our dataset. Now we need to add an image. We'll browse to the location, and Tableau automatically maps the axes to our fields, but we'll update the X field to the X. We'll specify the left and right as 0 to 840, and the bottom and top as 0 to 623. This essentially creates a scale along each axis of the image, which we can use to plot data later. We don't have to use the dimensions of the image. This could be any scale, but the dimensions are convenient. If the image is a map, use the appropriate range of latitude and longitude. On the Options tab, we'll click Always Show Entire Image. This keeps Tableau from adjusting the view, since we always want to see the whole MTR. To bring the image into the view, put the field map to the X-axis on columns and the field map to the Y-axis on rows. Next, we need to know the X and Y coordinates for each place we want to plot data. For us, that's the island line. Right-click on the first station and select Annotate Point. We can increase the size here and click OK. These are the coordinates that need to be entered into the dataset. To move to the next station, simply click and drag where the point annotation is pointing to. We'd repeat this for each point we want to be able to plot on our background image. In the interest of time, I'll copy all the relevant values that have already been recorded and paste them into the spreadsheet that we've connected to. Here we need to replace the dimensions that we already entered. We'll save this spreadsheet and go back to Tableau. We'll remove our annotation by right-clicking and selecting Remove. And now we need to refresh the dataset. This looks a little weird because we're currently plotting X and Y as sums. Let's break out the data by bringing Station to Detail. This will create a mark for each station. We can add line to color and edit the colors, matching the legend with purple and green. We can make the marks solid circles and add a black halo to make them really pop. We can right-click on the axes and uncheck Show Header to remove these axes from the view. We now have a nice clean background image with our points plotted. We invite you to continue with the free training videos to learn more about using Tableau.